Hello students, welcome to EPG Pathshala. I am Dr. Aranya Bhattacharjee from the School of Physical Sciences, Jawaharlal Nehru University. Today we are going to discuss about the module Electrons in Periodic Solids 2 under the paper Solid State Physics. So after studying this module, you shall be able to learn about the electron eigenstates and the respective eigenenergies. You will also know about the nearly free electron model and restrict to one dimension only. Learn about the energy levels in higher dimensions, learn about the degenerate energy levels in higher dimensions. Now, in the previous module, we had determined some general features of the eigenfunctions of a particle in a periodic potential. These have been derived using the periodic nature of the potential. We have set up the Schrödinger equation in the plane wave representation. This leads to a matrix from which eigenvalues and the eigenfunctions can be determined. It is clear that the realistic potential obtained in a typical crystal, the problem can only be solved numerically by employing some approximations. Now, by now some very elaborate and clever methods have been developed which solve the problem with great accuracy. However, a lot of physical insight can be gained by considering simple cases. Moreover, such simple considerations are very useful for understanding the detailed results of numerical computation. We now formally describe what we mean by the weak potential approximation. So we consider an electron in a crystal of sides n1, n2, n3 measured in the units of lattice constants. We also assume the same boundary conditions as we had been describing earlier. For simplicity, we start first with this 1D crystal, again for simplification, and the potential in this case has the form Vx is equal to summation over n minus infinity to infinity omega n b exponential iota n bx, where b is equal to 2 pi by a. And remember that omega 0, the average potential is set to 0. We again now employ the plane wave basis, and wave functions can be written as xi x is equal to summation over q aq into e raised to power I qx. Now substituting it in the one-dimensional Schrödinger equation, we get the following equation, that is the operator OQ minus E AQ plus summation over n minus infinity to infinity omega NB into AQ minus NB equal to 0. Whereas before, this operator is defined as simply the kinetic energy. Now from this equation, we can actually now write down the eigenvalue equation in a matrix form as shown here. We take Q to lie in the first Brillouin zone, that is lying between minus pi by a to pi by a. Note that as it must be, the matrix is Hermitian because omega minus b is omega star nb. Setting all the potential coefficients to 0 in the matrix above yields the unperturbed eigenvalues and eigenfunctions, and these are explicitly written in the following equations. So you can see that the eigenvalue corresponding to the kinetic energy h cross square q square by 2m, then the corresponding eigenfunction is 1 by under root of L. Now remember that this is normalized e raised to power I qx. Similarly, for the eigenvalue h cross square q minus b whole square divided by 2m, we have the corresponding eigenfunction 1 by root L e raised to power I cube minus b x. Again, for the eigenvalue h cross square q plus b whole square by 2m, we have the eigenfunctions 1 by under root of L e raised to power I q plus b into x. And finally, for the eigenvalue corresponding to h cross square q minus nb whole square divided by 2m, we have the eigenfunction 1 by root L into e raised to power iota q minus n times b multiplied by x. Zero order eigenvalues in the first Brillouin zone. The first few zero order eigenvalues in the Brillouin zone is shown in this figure, as you can see in this slide. Note that the higher eigenenergies are just parabolas, that is h cross square q square by 2m displaced through plus minus n times b. These are just free particles. Now why are these free particles? Simply because that it has only the kinetic energy. So these are just free particles energies plotted in the first Brillouin zone as would be required for this problem. So this does not have any potential, remember that now. So as you can see from here that this eigenvalues are only simply kinetic energies. The free wave vector k is written as k is equal to q plus minus g such that q is in the first Brillouin zone. Now we examine the effect of the lattice potential by the standard perturbation method by regarding the potential as weak. The first order correction to energy is En1, and this is written as that we take the expectation value of the potential with respect to the corresponding eigenfunction which n is found to be equal to 0 as omega 0 is equal to 0 as we had noted earlier. Now this means that we have to now go one order higher. The second order correction to the wave function and eigenenergy have the form as given by this expression. Now, where this MC depends on the labeling of the states as above, and the corresponding eigenvalue that you will have for the second order correction is given by this expression as shown here. Now, using the previous results as above, we first work out the energy correction to the lowest band of the state. Now, using the previous equation, immediately what we do is we get this E1 second order correction result. These corrections are quantitative and small except at the points where degeneracies happen. So in the second line we have to retain just the first two terms of the sum. Clearly terms for larger m are progressively becomes smaller. Divergence in perturbation approach. Now from these terms it is immediately seen that the perturbative correction diverges when q is equal to plus minus b by 2. These are points on the Brillouin zone boundaries and also points where zero order energies are degenerate. At these points and their neighborhood, the standard perturbation theory loses meaning as the energy correction is very large, even diverge, due to the smallness, vanishing of the denominator in one term of the sum. The remedy for this problem is that we have to treat the degenerate levels on equal footing. Let us consider the situation near q equal to b divided by 2, where q minus b whole square is approximately equal to q square. The wave function e raised to power I qx and exponential I q minus bx have an equal role and cannot be regarded as a perturbation on the other. At this order, we write the determinant for just these two levels, ignoring all other levels. This should be a good approximation for q approximately equal to b by 2. Following this, the resulting matrix is written as this, as shown in this equation. This is a matrix equation, and simply remember that this is simply just two levels, ignoring all higher order levels. Now continuing again in determining the solution at q equal to b by 2, we find that the solution yields the eigenenergies and eigenfunctions to be like this. So as you can see from here that we have got now two eigen energies, E negative and E positive, and correspondingly for these two eigenenergies we have the corresponding two eigenfunctions. So we see that E minus q is simply kinetic energy at q plus the kinetic energy at q minus b divided by 2 minus under root of del by 2 whole square plus omega b whole square, and the corresponding eigenfunction is cos theta by 2 into e raised to power I qx plus plus sin theta by 2 into e raised to power I q minus bx. And the other E plus eigenenergy now is also written in the same form, as you can see, and the corresponding eigenfunction is minus sine theta by 2 e raised to power I qx plus cos theta by 2 e raised to power q minus bx. So where this small delta is written as a short form of the kinetic energy at q minus kinetic energy at q minus b. Tan theta is described here. Note that this splitting occurs for any value of the crystal potential, however small. The two states are separated by an energy gap delta, capital delta, which is equal to 2 mod of omega b at q equal to b by 2. The degeneracy at other wave vectors are similarly. Next, we consider the case when q is approximately equal to minus b by 2. Now here one needs to consider the states exponential iqx and exponential iq plus bx. The matrix involved would be given like this. Now continuing with our solution again at q equal to minus b by 2 and following the same procedure as we did for q equal to b by 2, we get the following two eigen energies, that is E of E minus and E positive. Now see the difference, that if we compare this result with the previous case, the difference comes in where you have the kinetic energy now in E minus as Q minus B and E plus as Q plus B, and this here yields the energy gap of 2 omega B at Q is equal to minus B by 2. Gap also occurs at Q equal to 0, where the free energy states with wave vectors Q plus minus B are degenerate. In a similar manner, we can calculate the gap at Q equal to 0, where the free particle states with wave vectors Q plus minus B are degenerate. With crystal potential, these become E plus and E minus. The expressions for E plus and E minus are shown in these slides. And clearly we see a splitting. The two states are separated by an energy gap of twice of omega 2b at q equal to 0. Okay, so we will conclude the results that we got in the past few slides. So in the past few slides, basically what we did was that we tried to find out the eigenvalues for the q equal to plus minus b by 2 and 0. Now there are two features which have great physical significance in the previous slides. First is that the eigenvalues occur in bands separated by gaps, which is very clear from the E plus and E minus eigenvalues that we found out, and simply by subtracting the two we could actually find out the gaps. Within a band there are n eigenvalues. N basically indicates the number of cells in the crystals corresponding to the values of the wave vector allowed by the periodic boundary conditions. These are closely spaced for macroscopic crystals. The sizes of the energy gaps depend on the strength of the potential. Secondly, the energy for some bands increases as the function of the wave vector, while for others it decreases. So far, we have demonstrated these properties in one dimensions, which is basically quite easy. Before discussing the significance, we first establish them in higher dimensions. Energy levels in higher dimension. In dimensions higher than 1, it becomes difficult to depict the variation of energy with wave vectors. Even the free particle bands, which have simple mathematical forms, are non-trivial to visualize as function of the wave vector q, simply because there are many components of all the wave vectors. One way is to draw them along some typical directions and along lines joining significant points in the Brillouin zone. The other way is to draw some surfaces of constant energy at various representative values of energy. It is also useful to think in terms of the Fermi surface, which is the energy surface below which all states are occupied for non-interacting electrons at zero temperature. Energy of the Fermi surface is associated with the electron density or number of electrons per cell. Both ways are employed. In the following, we use the method of energy surfaces, which is particularly helpful in 2 dimensions. So we formally start with the method of energy surfaces. Now what one has to do is that first draw the surface in space around the origin q equal to 0. So these surfaces are drawn in a wave vector space around the origin q equal to 0. In this space, we also draw the reciprocal lattice. Now the unit area closest to q equal to 0 as drawn by the Wigner-Seitz construction is called the first Brillouin zone. The portion of q space with the area of unit cell which is next closest to q equal to 0 is called the second Brillouin zone. So in a similar manner, then the areas of higher Brillouin zones are identified. Like the next one, which is the third Brillouin zone, will be the one which is next closest to the second Brillouin zone, and so on. So then, as an example, you can actually try it yourself for the square lattice, that you can try to draw the first and the second and the third Brillouin zone, and in this way, the more difficult ones, the more difficult lattice you can construct. So now, according to the method that we described in slide, we will now try this for the square lattice. The first 4 Brillouin zones for a square lattice is shown in this figure. So now what one does is that, as you can see from this figure, that the first Brillouin zone is shown in the white and is described as like A here. Then immediately, again following the same prescription, you can draw the next Brillouin zone and the third one. So it is quite simple, as you can see. But now remember that if you take the full reciprocal lattice into account, this method is called the extended zone scheme. Now on the right, the small figures that we have shown here, portion of the higher zones are translated through appropriate the reciprocal lattice vectors G to form a compact shape. This is what is called as the reduced zone scheme. Now we again apply the method of energy surfaces and consider the free electrons as an example. So what we do is that when we are doing this method of energy surfaces for these electrons, consider a surface of energy E which is a circle of radius 2me by h cross square, and this is drawn with center at q equal to 0 in the wave vector space. Now if for small energy, consider that these electrons have small energy, the circle is entirely in the first Brillouin zone. Now let us suppose that the electrons that we have considered has got large energy. So naturally what will happen is that the radius will exceed pi by a, that is the edge of the first Brillouin zone, and this means that the states are now occupied in 2 zones, that is the first zone and the second one. So the states outside the first Brillouin zone belong to the band formed from the states of this kinetic energy, where G is plus minus 2 pi by a x plus minus 2 pi by a y. Now, as I had shown in the previous slides, the surface in 2 bands where the electrons with higher energy is occupied can be drawn actually now in the first Brillouin zone by changing their q vectors. That is, you bring the occupied levels of the second Brillouin zone and map it on to the first Brillouin zone. Now what was described in the previous slide, we show it in a schematic way. So as you can see that the first figure here shows the surface for a small energy E1. So as you can see that this small circle which we had drawn according to the prescription of the previous slide is contained in the first Brillouin zone. Now if you go to the next figure on the right hand side, you will see that surface for a large energy E2. Now you see the circle is not visible in the first Brillouin zone. It is going outside the first Brillouin zone, and the one which is going into the second Brillouin zone is not visible. Now go to the extreme right and you can see that what one has done is, in the reduced zone scheme now, that what surface was occupied in the second Brillouin zone has been introduced now into the first Brillouin zone by appropriate reciprocal lattice vectors, and these marked A, B, C, D actually originally in the extended billion zone scheme was occupied in the second billion zone, but now in the reduced zone scheme they are mapped onto the first billion zone. For three-dimensional crystals, a similar situation arises for the free particle bands. We take the example of a simple cubic lattice and draw the free particle energies in the brilliant zone. Then this is exactly what is shown here in this slide. So as you can see that the band structure is also drawn for the simple cubic structure, that is for the simple cubic three-dimensional structure. That is, we have plotted the epsilon k versus k. So as you can see the complexity of the energy bands in the three-dimensional case. And on the other hand, on the right hand side figure, we show the brilliant zone for the simple cubic lattice. Now again here what we are doing is that we are showing how a free particle band in 3 dimension looks like in a typical FCC lattice. So the left hand side figure, that is the A figure, is a plot of epsilon k, that is the energy as a function of the k vector, while on the other side, that is on the right hand side, we have the brilliant zone for the FCC lattice. We will describe not only the previous we will describe the previous slide, the slide 23, what this gamma, m, r and x denotes in the next subsequent slides. So just as an illustration, this particular slide 24 shows the FCC lattice structure of the brilliant zone and the corresponding epsilon k versus k. Now in this, what we do is that we try to describe in brief that how to plot the free particle energy curves in the simple cubic lattice as was shown previously. To plot these curves, the units of energy and wave vectors are taken to be h cross square pi square divided by 2m a square and pi by a respectively. The brilliant zone along with the label points was already shown previously. Now in these units, the lowest energy curves are, so like the first one that we take is the gamma x line. So the gamma x line indicates that what are the points, that the k vector is x 0 0, while the kinetic energy, that is O1 vector, is x square, where x lies between 0 and 1. Correspondingly, the xm line indicates that the k vector has components 1, y and 0, while the O1 vector is written as 1 plus y square, where again y lies between 0 and 1. Similarly, the mr line indicates the k vector as 1 1 z and the O1 vector as 1 plus z square, where again z is lying between 0 and 1. And finally, the Rx line is indicating the components of the k vector as x x x and O1 is 3x square, where as before x lies between 0 and 1. The set of next higher energy curves comes from the wave vectors with taking values 2 0 0, 0 2 0 and 0 0 2, and this will be described later. Now continuing from before, that is the next higher energy curves for the simple cubic structure is derived or found out in a similar manner as like this. That is, the first line that we have is gamma x line. So again k vectors have x 0 0. Now here note that the O1 vector is x minus 2 whole square. Similarly, the x m line has got the components of the k vector as 1y0 as before, but the O1 vector has changed as 1 plus y minus 2 whole square. The mr line has got the k vector 1 1 z, and the O1 vector is 1 plus 1 plus 1 z minus 2 whole square. And similarly and finally, the Rx line has got the k vector as x x x, and the O1 vector is x minus 2 plus x square plus x square. So this Rx line is triply degenerate, so any of the g vectors can be used. The free electron energy curves shown earlier for the FCC lattice are drawn along lines between special points in the billion zone. One can also draw the constant energy surfaces for the lattice. Now here we illustrate the constant energy surface for three different electron densities. So these are the Fermi surfaces for 3 different electron densities. For 1 electron per cell, the Fermi surface lies entirely in the first billion zone. For 2 electrons per cell, the Fermi surface lies in 2 bands. Now each portion is shown in the first billion zone. The hashed portion is the unoccupied part. For 3 electrons per cell, the Fermi surface lies in the 4th band as shown. So you can see that when one changes the electron density per cell, how the Fermi surfaces they change. That is, they change from the first to the second and second to the third billion zone. Next, we examine how the degeneracies of free particle energies occur in higher dimension and how they are split by the periodic potential. So, conditions for degeneracy. What are these? This happens when the vector O as a function of Q is equal to the vector O again Q plus the reciprocal lattice vector G. Q square is Q minus G whole square and 2Q dot G is equal to G square. So these are the conditions for degeneracy. All vectors Q which lie on a plane that bisects G perpendicularly satisfy the above equations. Degeneracy occurs for vectors Q which lie on the boundaries of the first billion zone. For larger G vectors, this corresponds to surfaces of higher billion zones which may also be regarded as higher bands. For a Q vector near the billion zone boundary, states exponential I Q dot R and exponential I Q minus G dot R are nearly degenerate. We again need to work in the subspace of just these two states. Repeating the same analysis as given above yields the following eigenvalues. E plus minus Q is equal to OQ plus OQ minus G divided by 2 plus minus under root of del divided by 2 whole square plus mod of Vg whole square, where the small delta is OQ minus OQ minus G divided by 2. So there are now two eigenvalues E plus and E minus corresponding to this sign plus and minus. Here Vg is the Fourier transform of the crystal potential. That is, Vg is the, as you can see, is written like this, that 1 divided by n Vc integral over the all volume exponential minus iq dot r Vr into exponential minus iq plus g dot r. The above equations imply that at the Brillouin zone surface, a gap of energy 2 modulus of Vg is opened. Since the Brillouin zone is made up of such planes where degeneracies of free particle energies occur, such gaps are opened up all along the surface of the zone. In higher dimensions, energies O Q minus G as well as zone are not isotropic, so free particles band overlap. The gaps as discussed above do not ensure that the crystal bands do not overlap. To ascertain the presence of gaps, one needs to obtain better solutions with numerical methods. And certainly, when you want to do numerical methods in condensed matter physics, you really need some very good workstations. An interesting point about the constant energy surfaces of these bands is that they always meet the billion zone boundaries perpendicularly. To see this, we set Q equal to G by 2 plus K and get the following eigenvalues, that is E plus minus Q. So as you can see that E plus minus Q is simply h cross square divided by 2m in brackets the vector G square, that is the reciprocal lattice vector, divided by 2 plus K square plus minus under root of in brackets h cross square G dot K divided by 2m whole square plus mod of Vg whole square. So where we have resolved K in components parallel and perpendicular to G. So in this, right in the next expression, like after this what I have said, you can see that we can now resolve it K value, the K vector, in components parallel and perpendicular to G. Now note that the derivative of the two eigen values E plus minus with respect to K parallel is 0 at K parallel equal to 0. which corresponds to points on the Brillouin zone boundary. This implies that the constant energy surface does not vary in first order as we move perpendicular to the Brillouin zone boundary. Note that this result has been derived in the weak potential approximation and need not be true for the true band energies. There are points where more than two Bragg planes meet, like corners of Brillouin zone where two or more planes meet. For wave vectors in the neighborhood of such points, more than two states are nearly degenerate. We now consider the shape of a constant energy surface with more realistic behavior than the Brillouin zone boundaries. A square or a cube lattice are easier to consider at first. We again fill levels with electrons and think of Fermi surface whose energy rises with filling. When the Fermi energy is below E1, the entire surface is within the first Brillouin zone. As the Fermi energy increases a little beyond E1, we note that the value of K should increase. But at the Brillouin zone, K parallel cannot increase and K perpendicular is given by this expression that K perpendicular square is equal to 2m into EF minus E1 divided by h cross square. Thus the surface is intercepted by each Brillouin zone, that is for a cubic lattice, forming a circle of radius K perpendicular. As the Fermi energy, that is EF, increases beyond E1 plus twice Vg mod of Vg, the energy gap is crossed and the surface extends to the upper band. This is exactly what is shown in this figure. For the surface in the upper band, the intercept on the Brillouin zone is again a circle of radius K perpendicular with K perpendicular square as 2m into EF minus E1 minus 2 mod of Vg whole brackets closed divided by h cross square. Another feature of higher dimension is that there are points where more than two Bragg planes meet, like corners of Brillouin zone where two or more planes meet. For wave vectors in the neighborhood of such points, more than two states are nearly degenerate. Now the above calculations would require working with a Hamiltonian matrix in the space of at least these states. So let us now summarize, students, what we have learned in this module. In this module, you have studied about the electron eigenstates and the eigenenergies. Now, the general problem of doing these calculations for realistic crystal potentials is very hard and requires the use of advanced numerical techniques. Now, why is this? Because there are so many electrons, so many ions that you have to take into account. Moreover, it's a three-dimensional case. When you have three-dimensional case, then you have 3n normal modes. So you see that n could be so high that the 3n becomes even higher. And analytically, this is not possible to solve. So we have to resort to advanced numerical techniques. But of course, using some approximation, realistic approximation, we can derive some basic analytical results, which we did. However, before launching into such calculation, it is important to develop some physical feeling about these states. Now, about an approximation in which crystal potential due to ions is taken as weak, then we study its effect by perturbation theory. So, I am sure the perturbation theory, which you are all familiar with, this is something very basic in quantum mechanics. So, this is also known as the nearly free electron approximation. So, you can relate this, the free electron approximation with the weak potential. So, if you have a weak potential, which naturally implies that the electron whose dynamics you are trying to understand is relatively free to move throughout the crystal. It is sort of delocalized. So, that is why we call it the nearly free electron approximation. Already at this level, one learns some general and important features of electron states in crystals. Though it appears that these states cannot be useful for quantitative purpose, it turns out that for a class of metals, full calculation yields results surprisingly close to the nearly free electron approximations. Now, See, this is again, it comes naturally because the weak potential approximation results in the free electron approximation, and the metals are the best examples to study this, because in metals the conductivity is extremely high as compared to other materials. So this basically implies that the electrons which are responsible for the good conductivity of metals are moving in a weak potential, and the electrons, the same electrons, are relatively free. So that is why we have the nearly free electron approximations. So that you can see that now the comparison, the link, weak potential, nearly free electron approximation, and then you have the metals. About the concept of extended zone scheme, you learn reduced zone scheme with respect to the Brillouin zone. So, well, I mean, in this particular concept, you learn how to actually draw and look at the energy level diagrams, the band diagrams in the reciprocal lattice. Various ways of doing it. One is the extended zone, that is basically the full zone, first Brillouin zone, second Brillouin zone, third, fourth, and so on, you can draw. But then it becomes very tedious to go beyond the first or second or third, fourth. Then we resort to something, a simplification, because we have already learned that any vector which goes beyond the first Brillouin zone can be brought back to the first one by simply using a convenient reciprocal lattice vector. So this means that instead of using the extended zone scheme, we could actually use a reduced zone scheme. And then you also learned the constant energy surfaces for three different energies in a square lattice, the simplest case. Thank you very much.